Hello and welcome to Expert City. Please like, subscribe, and hit the bell icon to stay tuned. Today, we're going to talk about retrieval augmented generation, commonly called RAG. What is RAG, and why do people confuse it with fine-tuning? Let's try to understand RAG by differentiating it from fine-tuning to fully understand its utilities. In both cases, you're using external data to make the model results more targeted and better for that particular application. In the case of fine-tuning, what you're doing is feeding that external data to the LLM so that it can directly answer any questions in that particular arena. In the case of RAG, however, you're not passing this data directly to the LLM. Instead, you create something called a vector database, which makes it very efficient to store and search information. And when a question is posed, it's not directly given to the LLM, but to a separate system called a retriever, hence retriever augmented generation. And so this retriever does a similarity search between the question and the vast vector database that it has to provide a context of matching searches. So the question, along with this context of these sources of truth, are passed on to the LLM, which then gives you an informed decision. In cases where it cannot find any results from the vector database, programmers have the option to just bypass the entire LLM and to mention that there is no relevant search. The advantage of this is that you can prevent hallucinations with LLMs. So what do we gain from using this new technique called RAG, especially over fine-tuning? The first thing is that the information isn't directly being fully loaded onto the LLM. The LLM is not being trained on this information. And so because it's a need to know sharing of data, you have a higher level of data integrity. Also, you're not retraining or fine-tuning the LLM, which is excellent when you don't want to use too much of compute power, which can be very expensive. And yeah, we reduce hallucinations as we talked before. Even in the case when there is a match, because it has that particular context, the LLM works much better and is much less likely to hallucinate. So, in our live example, I'd like to share with you the data we used. So this data is from Patrick B, so a huge shout out to him. And it's about the Indian Premier League, which is the biggest cricketing tournament in the world. Now this has two CSV files, and I've used the one called matches.csv. So it contains all of the matches played in the IPL with columns including the date it was played, the two teams that played, the team that won the game, the margin it won by, and so on, where it was played as well. So I've split it into individual years, and for the purpose of this assignment, I've chosen just 4 years, 2021 to 2024. Just to make it easy, you could have even more years if you'd like. So this was manual splitting. I didn't use any fancy technology. I just took all of the rows that contained that particular year's matches and copy pasted them into a separate CSV file. And the two main processes I use, the main models I use, are one called text embedding adder from OpenAI, which converts text into vectors. Now you might wonder why the vector is much bigger than the text, but this is because this vector is operating at a higher dimension. This means that similarity searches become much easier and patterns that are otherwise unseen get seen in this model. The second one I used is FAIS, or Facebook AI Similarity Search, which uses indexing to quickly identify similarities between the query and the vector database. So here's a quick overview of the setup and the process. And the thing you can see right now is the setup. So each match summary is converted into a dense vector using the OpenAI model. And these embeddings are added to an index. You have one index per year. And on the query side of things, when a question is asked, the query is again converted into a vector using the same OpenAI model. And then FAISS compares the query with the data that we have stored. And if there is a match, it identifies the most similar embeddings and passes this information along with the query to the LLM to get a response. Otherwise, you just say, hey, you know what? We couldn't find any data, so we're not going to move forward. Let us now look at the code in implementation. So in the beginning, you can see a lot of pip installs, and you can see a bit of version control here as well. This was only because I was having some problems with certain libraries being at an advanced stage than other ones. But technically, once you have all of these installed and resolve any version conflicts, you can import them and load the files. So we have one CSV for all of them, as you can see. And this is just to convert each, let's say, row into a more usable format, kind of like a JSON format, which is easier to operate on. So as you can see here, it loads the data. And what's happening here is I'm creating a new column called summary for each row. So it takes all of the columns, for example, the season, the year which the match happened in, the city, the date, the match type, and all of these details. And match type just means that it's either a league match, a qualifier match, or a final match, and puts it into one column, which can be used for easy embedding instead of embedding multiple columns, which takes up a lot more space. Just have one compact column that it can work with. And this is creating the embedding model. So it converts the text into a vector. For example, if I take any random string, this could be anything here, it's going to convert it into a dense vector as such. Now, I'm going through each year and going through the data, and I'm converting the summary into an index so that it can be stored as an embedding and an index for rapid fast searching. Now, I don't particularly need the other columns when I'm searching for the row. It can just be used to identify the row, and then I can extract the information later on. And that was the configuration. Now we can look at running the question per query. So when you look at this function here just extracts the relevant information from each of the rows once it identifies that this is the row I want. For example, I'm loading the index, the relevant data, and I'm searching for the particular row and extracting that information of that particular row here. And I've added two clauses as well. You can filter by, let's say, the year in this case, or you can filter by the team just to make it even more relevant and easier for the tool to operate. And so this is to generate a response in case there is a result. I tell the LLM, in this case ChatGPT, that here's the context, which is the information I've extracted from the document, and here's the actual question to begin with. And so that's what this is doing. It's inputting the context and the system, and it's getting a response. This would be the response from ChatGPT. And so here's an example question. Now, if anyone follows the IPO and is a fan of the SRH, they're going to love this match. So here's a little Easter egg. But yeah, it collects all of the information and it prints the results of the relevant documents. Because there is a result, I'm going to send it to ChatGPT and catch its response. And so it tells you how much it won by and what has happened. It has all of the details necessary. And so after this, I decided to just put it in a loop so that you can ask multiple questions, and that's exactly what has been done here. So I type in the question I want, for example, what is the greatest margin of victory in IPO 2024? And then I've entered 2024 so that it focuses on that particular year. It goes through all of the matches then, identifies the relevant documents, and if I go up here, yeah, the greatest margin of victory in IPO 2024, was the CSK versus Hyderabad match. And so that's how you get these effective responses using RAG. Thank you so much for tuning in, and I'll catch you at the next one. And as always, you can find the data in my GitHub repository.